Hello, welcome to a deep learning approach for COVID-19 trend prediction. In this paper, we want to answer the following questions. First, what kind of method should we choose to efficiently model COVID-19 pandemic? Second, what kind of information should we choose in order to make the prediction? 3, how to properly evaluate the prediction? 4, can we interpret the relevance of the environmental factors to the model? The ongoing pandemic of COVID-19, which started in late 2019 in Wuhan, China, has spread around the world, disrupted our daily lives, affecting more than 225 countries. As the date of July 27, 2020, we have about 16 million confirmed cases. There are about 648,000 disease cases and about 9.4 million recovered cases. To effectively model the pandemic, there are two directions of epidemiology models. The first direction is ODE-based compartmental model, for example, SIR, SEIR. This kind of models usually doesn't have high precision, normally difficult to adjust to time-dependent scenarios, such as change of the environmental factors. The other direction is deep learning-based nonparametric approach, which normally have better prediction powers, but highly dependent on what kind of data it used to select in order to make the prediction, and also what kind of deep learning architecture to choose. Our approach for trend forecasting is letting the environmental factors to dynamically facilitate the modeling and prediction of the pandemic evolution. The following list describes the environmental factors included in this work. We have population density to describe the total population of the state. We have GDP per capita to describe the economic of the state. We also have age structure within the state of the different age distributions. We have the restriction orders to describe the state policy with respect to the ongoing pandemic. We also have high-risk population rate. We have annual employment, which describes the airline traffic feature of a certain state. We also have the risk structure, which is the different risk distributions among states. All of these environmental factors are fitted into epidemic time series in the following structures. We choose linear embedding to distributedly represent the environmental factors. We choose the RNN model with a sliding window size of 5 to model the epidemic evolution. To connect these two, we use the Kickstarter mechanism, which described later. Here is a diagram of our model architecture. In the beginning, we have the environmental factors. The factors pass through a linear embedding, and the output is duplicated into 3 copies. Each of the copy fitted into one layer of GRU units. The GRU units take the embedding value as their initialized value, H0. The 3 layers of GRU slide through a window size of 5. During each of the window day, we have 4 channels of inputs. We have CC, which stands for cumulative cases, representing how many cases have accumulated of that state. DC represents a delta of confirmed cases, which represents number of new cases are occurring in that state. DC values all from prior day. And then we also split the CC and DC corresponding to their with restriction version and non-restriction version. Thus, we have 4 channels. After sliding through the 5-day, the GRU output latent feature. We add an output layer, and the objective is the new case at time t. The first evaluation method is one step ahead prediction. The model is given a 5-day window of input as well as the environmental factors. The model is trying to predict the next day new cases. The diagram on the right side shows the 4 states in the test set: New Jersey, Missouri, and South Carolina, and Arizona. We can see the prediction and the ground truth overlaps pretty well. The second evaluation method is a long-term prediction. Up to a point, we let the model stop using the ground truth input and use autoregressive values to serve as future input. You can see the vertical blue line is the point that we stop using the ground truth of the input, and the future of the output serve as the future inputs. Finally, since we have the embedding module, we can check the relevance of the environmental factors to the model. Here, we extracted the weight average from the embedding module. And on the right side, the diagram shows the top relevance index in both age factors and the risk factors. We hope our work sheds some light to effectively model the ongoing pandemic, also gain some insights of how environmental factors are contributed to the model. Thank you.